Mhm. Okay, so what we're going to do is we are going to complete an entire past paper. And as we come across questions we haven't covered in detail for mechanics, I will go on a tangent and explain the topic. This way it's a lot more efficient. I just feel like it's a lot more neat as well than me explaining the topic, then the question, and the topic again. So we'll save a lot of time doing this as well, which is kind of what we need because there's only like 7 weeks left until your exam. Okay, so question 1. Quantities in physics are classified as either vectors or scalars. Which of the following units could only be used for a scalar quantity? Have a go at this, Muhammad, and when you feel like you know the answer, let me know.
So if if it's ms minus 2, what does it mean compared to the ms minus 1?
What has units ms minus 1?
Meters per second. So speed.
Speed's a scalar. How about
Yeah.
velocity?
Yeah. Would velocity also have ms minus 1?
Good. And because velocity has the unit, because this is distance over time, right? Or displacement over time, then A is incorrect because A can also be used for a vector, right?
Yeah.
So it's not A. How about meters per second squared? What has that as its unit?
Acceleration.
Is that a vector?
No.
Does acceleration have a direction?
I'm not sure actually.
It does, because minus 9.81 in Suva, the fact there's a
Oh yeah.
minus shows that there's a direction. So acceleration is a vector, so it can't be B. How about kilograms meters per second squared? What may have the following units?
Force.
Beautiful, force, because this is the same as mass times acceleration, okay? So is force a vector?
Yeah.
Can't be C. So through process of elimination, the answer is D. However, I want you to tell me what quantity has the unit kilograms per meter cubed?
Um. So kg comes from mass.
Good.
Wait. Yeah. Kg comes from mass.
And m cubed?
Volume. So it must be density.
Beautiful. This is mass over volume. So it has to be density. Hello, Isa. Hello, Fazan. So we just did the first question. And the question was, which of them could only be used as a scalar? And Muhammad answered this masterfully. Muhammad said the first one, meters per second. Oh, that's velocity, right? Velocity is a scalar, so it can't be A. Meters per second squared is acceleration, which is a vector, so it can't be B. Kilograms meters per second, he noticed kilograms is mass, meters per second squared is acceleration, which is force, and force is a vector, so it can't be C. And then finally, kilograms per meter cubed, which is mass over volume, which is density. It is a scalar, and there's no vectors that have this unit. So through the process of elimination, D is the answer. D is the only thing that could only be used as a scalar. There's no vectors that have that unit. Does that make sense? Isa, Faizan, we following?
Yeah.
Excellent. All right. So question 2. By the way, we're going to start past papers. And as we come across a topic that we haven't covered in detail, I'm going to go on a tangent and explain it in detail. This is going to be a lot more efficient. It's going to save you guys a lot more time. And it's going to allow you to finish earlier because there's only 7 weeks left until your exam. As we started a bit late. Okay, so once in orbit above the Earth's atmosphere, the engine on a space rocket are switched off. Which row of the table correctly states the resulting motion of the rocket and the law explaining this motion? I'll give you 20 seconds to read and form an opinion. Okay, Faizan, what do you reckon?
So you're gonna give me a minute because I was getting my notebook.
Oh, okay, no problem.
So I'd say it's B.
You're saying it's uniform velocity? Okay, the engine's switched off and the rocket's above the Earth's atmosphere. Is there a force acting on it?
I mean, actually, yeah, no, because it's not in the atmosphere anymore.
Does something have to be in the Earth's atmosphere for gravity to act on it?
No?
Good, no, it doesn't. Okay, can I have a look at that?
So then,
Yeah,
if it doesn't have to be in the atmosphere, then I'm guessing it's C. I
good.
think.
It will be C.
Yeah.
Because there will be the force of gravity acting on it, right? Earth's gravity is going to act on it. So there is a resultant force. Therefore, there is a acceleration. Changing velocity means acceleration, which is Newton's second law, F equals ma. And we're just going to do a quick little tangent on Newton's laws. So what's Newton's first law? Let's have Asa answer this.
Newton's first law is like if an object does not have any external forces acting on it, if it's stationary, it will stay stationary, and if it's moving at a constant speed, it will continue to move at a constant speed.
Good, so an object continues traveling at uniform velocity. The velocity could be 0, i.e. stationary. Okay, right? That's still uniform velocity of 0. So an object continues traveling at uniform velocity as long as there is no resultant force acting on it. We love to use the word resultant force in physics. So if there is no force, nothing will happen. It will continue doing whatever it was doing. What's Newton's second law, Muhammad?
That's the F equals ma.
Good. Newton's second law is the opposite of Newton's first law, which is if there is a force, it will accelerate. So F equals ma. This is literally the opposite. First one is there's no force, it won't accelerate, nothing will happen. Second one is there is a force, it will accelerate. Okay. So we're going to add a little bit of commentary. If there is a force, resultant force acting on a mass, it will accelerate. Good. And finally, Newton's third law. What does this one represent? Faizan?
Every action has a reaction equal in magnitude and opposite in direction.
Every action has a reaction. So if I start shouting at you, you start shouting back.
Oh, so
Every
I mean that's
action
has
act
an
what? Action what?
wait,
Action velocity, action momentum,
force,
action.
right?
Good. For every action force, there is an equal brackets in magnitude and opposite. You have to say equal in magnitude and opposite brackets direction, because equal and opposite in what? Equal in velocity and opposite in momentum, right? So you have to specify. There's an equal in magnitude and opposite reaction in direction force, okay? So this is Newton's third law. This is the shortest way you could phrase it by getting full marks. And then finally, we're going to talk about a little trick for explain questions. Really, really important for explain questions. And you know what? I'm going to teach you this, and you're going to somehow forget when we do another question in the future. I'm going to call it from now. It always happens. So try and prove me wrong. So here's the little, I don't know, diagram, I guess. The question is there a resultant force? This is the question. So let's put it as a little cloud. The answer is yes. In fact, let's start if the answer is no. If the answer is no, that means you're talking about Newton's first law. That's the law that matters, right? No resultant force will continue doing what it's doing. That means acceleration is 0. Is 0. Good. Now, if the answer is yes, then we're talking about Newton's second law. F equals ma if it's a calculation question. You need to be thinking about this, or if it's a question that involves equation of motion. And then finally, there is acceleration. So these are things you have to talk about and think about for every scenario in physics that involves forces. When it involves anything really. Is there a force? Is there a resultant force? No. Okay, Newton's first law, no acceleration, nothing's going to happen, easy peasy. The answer is yes. Oh, it's going to accelerate. F equals ma, Newton's second law, and other stuff you could add to this diagram. So these are the skill sets, by the way. So what I'm covering right now are the skill sets we've learned, and they're worth writing down after doing a question. And if you want to get an A in physics, my advice is to do like 5 or 6 past papers, where for every single question, you write down the skill sets, as I'm going to try and do with you guys. Okay, so the answer will be C. Why? Because there is a force, so it's Newton's second law, so it's accelerating.
So I have a question.
Yes.
So are we done with the whole syllabus and tuition? We finished?
Yes and no.
So what do we have left for Unit 1?
So there's inclined planes, there's, I guess, efficiency and work done. Like there was a session where I briefly covered everything, very briefly, but there are just little details that I will cover as we do the past paper questions.
I mean, sir, to be honest, like we did it in class, and if everyone's fine with it, we could just do past papers instead. It's more useful.
Yeah, that's what I want to do. That's what I've decided we're going to do anyway. Yeah.
Yeah. Okay. Then that's
just because there's 7 weeks left, and realistically, it might even take us 2 sessions to complete 1 past paper at the start. So that's 1 week to do 1 past paper. There's 9 past papers that I'm going to send to all of you, and there's only 9, by the way, in the new syllabus. I can't send you the 2022 ones, just because you know they might use it for your school mock, so it's technically illegal. But I'll send it after your mocks, and then that's 9 full past papers, and each one has a examiner's report as well. And we'll try cover as much as possible. The more we cover, the stronger you're going to feel. So I feel like once we covered the 4th past paper, here's like my prediction. After we've covered the 4th one is when you're all going to start feeling confident. Like, you know what, actually, I might get a good grade in physics. But I feel like for the first 3, the first 4, you might be like, oh, this is too hard, which is normal, by the way, because in these ones, we're going to cover the skill sets as I'm doing now. And we're going to realize that every question involves you talking about these skill sets. So question 3, which of the following is the minimum value
Sir?
of f? Yes, Isa.
Sir, can you explain question 2 again, please?
Okay, so question 2, what it says that once in orbit above the Earth's atmosphere, and by the way, it's in orbit, right? It's in orbit. So technically, you know, of course, there's going to be a force, the centripetal force, but that's not really in your spec, the centripetal force. That's for unit, for year 12, year 13, if you're doing that. But yeah, there is a force acting on it. There's the force of gravity. The engine switched off, meaning there's no other force. It's just the force of gravity. But the key thing is there a resultant force? Isa? Is there a resultant force acting on the...
Yeah, I think
rocket?
there's like a resultant pulling it towards the Earth.
Good. It's weight, right? The force of gravity, which is weight, is pulling it. That's the resultant force. So going back to this, there is a resultant force. That means you're talking about Newton's second law, which is if there's a resultant force, an object will accelerate. Okay. So there is a result.
So any object in space still has a gravity acting on it towards the Earth?
Yeah.
Like
How do
anywhere
you...
in space?
Not anywhere in space. The further away you get from the planet, the weaker the gravity.
Okay, so how would you know that this object maybe let's say it's far away? So they didn't specify in the question.
Again, you would know if you've done year 13. In year 12, they're not going to test you on anything that involves that. You won't need to know.
Okay.
You would just, oh, it's next to Earth, or it's, you know, somewhere around the Earth, or it's orbiting the Earth, then there's going to be gravity. That's it. That's all you need to know. So yeah, there is a force. So there is an acceleration. So it had to be changing velocity. So it's either C or D. And I know that changing velocity or acceleration has to do with Newton's second law, not Newton's third law. And Newton's third law, while we're here, we might as well just do a little recap of Newton's third law. The forces, the action and reaction forces, the forces come in pairs. What does that mean? It means there's always two forces. So there's always an action and reaction. That's a pair, right? Just two. So the forces come in pairs. And the second really important thing you need to realize is they act on separate objects. And yes, this is for every single action force that exists. And I'm going to prove that right now. Let's say you're standing on the floor. Weight is pushing you downwards, correct? So there's mg going down. Why are you not accelerating downwards if there's a force going downwards? What's stopping you from falling into the floor? Faizan.
So can you repeat the question?
When you're standing on the floor, right? You know that gravity is pushing you down, correct? But what's stopping you from accelerating downwards? Why do you stay on top of the floor?
Because the ground, like you can't go through it. What?
In terms of physics.
In terms of it.
Which Newton's law?
So would you say Newton's third law and the ground is exerting a force back on you?
Excellent, beautiful. This is Newton's third law. There was an action force, you pushing on the floor, so the floor is going to push back on you. You are pushing on the floor is pushing back on you. The forces are acting on separate objects. It's not like both of the forces are acting on you or both of the forces are acting on the floor. One force is acting on the floor, the other force is acting on you. Does that make sense by they act on separate objects?
So it's the same type of force, right?
Same type of force, yeah.
Okay.
I'm going to add that as well. Also, same type of force. Beautiful. Another example of Newton's third law is, let's talk about the rocket that's now in orbit. there is mg weight pushing the rocket down. That means there has to be mg pushing the Earth up. This is an example of Newton's third law. So there's a force acting on the rocket and there's a force acting on the Earth. It's the same type of force, it's gravity, the force of gravity, same type of force, the same magnitude, opposite directions, it's a pair. This is Newton's third law. So actually when you jump and the Earth pulls you down, you're pulling the Earth back up. But the Earth hardly moves because applying a measly 700 newtons on the Earth is not enough to cause it any change, right? Especially when the Earth weighs a billion kilograms. Does that make sense? Obviously, I made that number up. But yeah, so this is another example of Newton's third law. Another example is maybe you have two magnets, a north and a south pole. This is going to pull this one with a force. This is going to pull this one with a force. Equal in size, opposite in the direction, same type of force. They're acting on separate objects. There's a force acting on the south pole and a force acting on the north pole. Are we happy with Newton's third law? Yes, no?
Yes, sir.
Okay. If you have any questions, just let me know. So yeah, let's now begin question 3. A sphere of weight 2.5 newtons floats in water with half of its volume beneath the surface. A force F is applied to the sphere, completely immersing it in the water as shown. Which of the following is the minimum value of F?
So is it C?
Why do you say C?
Actually, wait, let me think for it again, wait.
So it's B, right?
It is B. It's B, and the reason is, notice half of the volume is underwater. Okay? And if I were to draw a force diagram, what are the forces acting in the sphere? There's weight, which is mg, and there's upthrust. And it's balanced, it's floating, so I could say that mg is equal to upthrust. Now, that means if I want to fully submerge it, instead of half of the volume being underwater, and remember, upthrust is the weight of fluid displaced. So how much water is displaced and the weight of it. Right now, only half of the volume is underwater, so only half of the weight of fluid is displaced. To displace the other half, you're going to need another mg. And I know that mg is upthrust, so it's going to equal to 2.5 newtons because that's the weight. So to cause the full sphere to be underwater, then you're going to have to apply another 2.5 newtons. So the answer is B. Right, because upthrust is 2.5 newtons, but this is only for half of the volume. I know if I displace the other half, then the upthrust is going to double. Have you ever had a bouncy or like a beach ball on water? It floats, right? I'm sure you've all seen this or played with this. And then you try to push it underwater. The more of the ball that's underwater, the larger the force pushing upwards. Who could relate to this example?
Yeah.
Good, excellent. So yeah, why? Because the more of the more of the ball underwater, the larger the volume, the more fluid displaced, the more weight of fluid displaced, the more upthrust it is. So that's why it's really difficult to put it all underwater. And it will require twice the force to put the other half. So another 2.5 newtons is required. Because the question is not asking what is the total force, it's just saying how much extra force. The total force is indeed 2 times 2.5. So a lot of students would have accidentally misread and didn't bother reading the question carefully. So they would have said, oh, it's 2 times 2.5, which is true, that is the total, but it's not asking for the total, it's asking what extra force do you have to apply, which is just going to be equal to the out thrust. Beautiful. So a ball rolls off a table with a horizontal velocity of 1.2 meters per second. And before we even do this question, what type of question is this? What topic?
Projectile motion.
Good, SUVAT, right? This is a SUVAT question, very clearly. And it says the ball takes 0.9 seconds. So it's giving me time. It's giving me horizontal velocity. So I'm probably going to have to solve a horizontal SUVAT. And always in SUVAT, when you're working horizontally, you use the equation S is equal to U times T. It's technically S equals UT plus half AT squared. That's technically the full equation, but we know the acceleration horizontally is 0 because there was no force horizontally to cause it to accelerate. Obviously, vertically, there is a force. That's why the acceleration is minus 9.8. So this is always the equation for a horizontal SUVAT. It's in which of the following can be used to determine the value of S? Well, again, we just said S is equal to U times T, which is 1.2 times 0.9. Very simple question. It should have took you like 10, 15 seconds in the exam. Don't spend longer than you need to, because you need time for other questions that are harder. Okay,
Sir, I have a
Assam?
question.
Yes.
So it's not about the question itself. So if you want to get full UMS, what do you need, like the raw mark? Usually, what do you have to get?
It depends on the scaling. So generally, there's this rule that 70 is equal to a B, 80 is equal to a 90 is equal to A star, and 100 is full marks. That's like a general rule. Obviously, in a real exam, it depends on how difficult it was. So sometimes 43 out of, is it 80, I think? 43 out of 80 is an A, okay? So they do a scale. And if that's the case, full UMS, 120 out of 120 will probably be around 68 out of 80 in this sort of case. So by getting 68 of the marks, you got full UMS. I remember you only need 96 out of 120 UMS to get an A. So something like that. Obviously, it depends on the exam. The COVID exams had really, really low grade boundaries. I think one of them was like 38 out of 80 for an A. But now the grade boundaries have recovered because the effect of COVID's over. Does that answer your
So it's
question?
either,
Yeah.
it's either 120 UMS or 80, and that's all you can get, right?
What do you mean?
Like, so you can get any number UMS, because I looked at the grade boundaries and it's either 120 or 80.
Yes, you could get full UMS by getting like 65 out of 80.
Okay, that's pretty high.
Yeah, but you don't need 120 UMS to get an A. You only need 96 UMS, which is around maybe 50 out of 80 on average. I don't know. I think like 63% is the average of the last 5 years or something to get an A. Okay, so let's carry on. A sample of sea water is collected using a beaker. The sample contains some particles of sand, which settle at the bottom. Which of the following would result in a decrease in the time taken for the sand to settle?
D, right?
Can you explain why?
Because if there's lower viscosity, there's going to be less viscous drag, so time taken is going to fall faster.
Excellent. And you know what? Let's see why A, B, and C are incorrect. If the smaller particles, they will travel slower. And this is something you need to know. So if you have like a beaker with some sort of liquid, a smaller particle or a smaller sphere, right? Sand could be modeled as sphere. A smaller sphere travels slower. If you have a larger sphere, it travels quicker. And if you've done the experiment in school, your teacher would have showed you that's the case. And that's why in the required practical, you have to use a small sphere Why do you want a small sphere? So it takes long to fall. So you have a large time. So you have a smaller percentage uncertainty. Good. So the first one is not true because the first one is going to make it travel slower. So that's going to increase the time taken. Lower temperature. Well, if it's a lower temperature, it's more viscous. If it's more viscous, it's going to take longer to settle. Smaller terminal velocity. Well, obviously, if it's a smaller terminal velocity, then it's going to reach the terminal velocity quicker and it's going to travel more slowly. The average speed is going to be less. So A, B, C cannot be correct, and D is correct because less viscosity means it's going to travel faster through it. It's going to have a higher terminal velocity. Okay, beautiful. A graph of stress against strain up to the breaking point is drawn for 4 samples of wire A, B, C, and D. Which sample of wire has both a low elastic limit and a large region of plastic deformation? Is it A, B, C, or D?
So is it C?
It is indeed C. Muhammad, can you explain why it's C?
Yeah.
Go on. Why is it?
So you put.
Yeah, sorry.
Wait, so can you say what you can you ask the thing?
No. Carry on.
So you're putting more strain. There's obviously more strain.
Okay, but how does it show it has low
So-
elastic limit and large plastic region?
Because plastic region means it doesn't break as quickly and it stretches.
How do you represent
say
the
it
plastic
stretches?
region? How does the plastic region look like in a graph?
It's long against the stress.
It's the area under the graph after the elastic limit. Meaning,
Okay.
let's say this is the elastic limit. So after this point, it's no longer going to deform elastically. This is your plastic region. So the energy is now used to deform the material instead of the energy being stored. In the elastic region, the energy is stored in the spring. And when the force is removed, the energy is used to return it to its original shape. But in the plastic region, the energy is used to permanently deform, change it. So clearly, A and B have really large plastic regions compared to C and D. So it can't be A or B because they have large plastic regions. But you want a low elastic limit. D has a really large elastic limit. Look, the elastic limit is all the way here. That's where it's no longer a straight line. Whereas C, the elastic limit is here. So C has both a low elastic limit and a large region of plastic deformation. Because look at this. This is a large region of plastic deformation and it has a low elastic limit. A has a large elastic limit and a large region of plastic deformation. Wait, my brain stopped working. Let me just... Low elastic limit. So yeah, let's draw the elastic limits for each one. This has an elastic limit here. 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 So both A and B have low elastic limits, right? So the answer cannot be B and it cannot be D. However, A has a larger plastic region than C. So the answer is actually A. The answer isn't C. You confused me. Who confused me? Faizan. The answer is A. Does that make sense though?
So I don't get why it's A and not C.
Because it wants a region with a low elastic limit and a large plastic region, right? Look at C's plastic region. C's plastic region is this.
So can you explain what plastic region is? That's what I don't get, I think.
So in a stress strain graph, you have the region where Basic law, then you have the limit of proportionality, then you have the elastic limit, right? You understand what elastic limit is?
Yeah.
Then you have your ultimate tensile stress and blah, blah, blah. Okay. Now, before the elastic limit is the elastic region. What's the elastic region? It's when the force is removed, it returns to its original shape. Does that make sense?
Yeah.
If you stretch a shirt, it goes back to its original shape. After the elastic region is the plastic region. Plastic region meaning once you apply a stress above this, what ends up happening is it gets permanently deformed. It doesn't return to its original shape. Does that make sense?
Yeah. And so what does it mean to have a large region of plastic deformation?
Okay, so the area under a stress strain graph, the area under is the energy, the work done. So after the elastic limit, the area under the graph, just after, not before, is the plastic region, meaning the energy that you're giving to stretch it. When you stretch a material, the energy you're now using in this region is used to deform it, is used to change the arrangement of the atoms and layers. And the shape will not return back to its original. Khalas, you permanently bent it. Kind of like, let's say you had a metal rod and you bent it, right? The energy is not stored in the rod because once you remove the force, it remains there. You've permanently deformed it. You've now used energy to deform your metal rod or your paper clip, whatever that is. And if you keep bending it, you keep providing energy and you keep deforming it. And if you bend it too much, eventually it breaks, right?
So basically what it means is to have a large region of plastic deformation, it needs a lot of energy to permanently deform it.
No, it needs a lot of energy to break it.
Oh, to break it, and permanently deform it is in the elastic region, right?
No, permanent deform is in the plastic region.
Wait, so large region of plastic deformation means it needs a lot of energy to break it, but if it's in the elastic region, it needs a lot of energy to like stop it from returning back to its original shape, right?
Okay, I'll try to explain this one last time. So, like the Microsoft Paint. Here you go, limit of proportionality. Maybe you got the yield point, the blah, blah, blah. Let's say this is your, on red, this is your elastic limit. So let's call it EM. Let's draw a straight line downwards. Okay, so before the elastic limit, and let's shade it in red. Before the elastic limit, the energy you supply to a spring or a material or a shirt, whatever it is stored inside the actual material. So if you stretch the shirt and you've applied a stress before this elastic limit, the energy is stored inside your shirt. When you let go, that energy stored is used to return it to its original shape. So far, so good?
Yeah.
After the elastic limit, and by the way, the energy you're given is the area under the graph. So let's say I applied a stress of sigma over 2. So around here, I applied the stress around here. The energy stored is this purple, this area under the graph. Okay, that's the energy stored in the spring when you apply that much force. So far, so good?
Yeah.
Now, after the elastic limit, and by the way, this is called the elastic region. This is called the elastic region. Elastic region. Energy is stored in the material. So in the elastic region, anywhere in that region, the energy is stored in the material. After the elastic region is what we call anything in this region here is the plastic region. And in the plastic region, the energy supplied, so let's say you applied a stress of, I don't know, let's call this X pascals. If you start applying a force of above X pascals, the energy you're giving to the material is no longer stored. It can't store any more energy. That extra force, the extra stress, the extra energy you're given, and is now used. Energy is now used to permanently deform the material. So the shape's going to change forever. Does that make sense?
So basically, the energy now is going to be used to just deform it and then
Yeah.
eventually just break, right? That's it.
Yeah, the material can't store any more energy. It can't store. It's reached this limit. It's called the elastic limit. After that, the energy is now going to be used to actually change the shape.
So before it was stored to just stretch it out, but now
Mhm.
that it's past that limit, it's used to deform it, and then eventually it's just going to break. So if you want a
Yeah.
large plastic region, it
Yeah.
uses a lot of energy to deform it and then break it.
Good. Excellent.
Okay.
A large plastic region means it could absorb a lot of energy before breaking. Look at the area under the graph is the work done, the energy stored. There's so much area under the graph, meaning you could deform it again, twist it. You could keep deforming it. You could keep changing the shape. It's going to keep absorbing energy. Eventually, after like the end, it would have broke, right? It would have reached the tensile stress or whatever, it would have broke. If a material has a small plastic region, like let's say like this, the plastic region is small. You know what that means? Okay, you could bend it a few times and then it will break straight away. You can't deform it that much. It can't absorb that much energy before breaking. Wood is going to have a really, really small plastic region. Can you bend wood? Can you deform wood? Change the shape? No. So it will break instantly. It can't store any energy. It can't deform. So it's going to have an almost non-existent plastic region. Whereas a metal wire is going to have a really large plastic region because you could keep bending it, twisting it, coiling it, and it's going to absorb the energy before it breaks. Does that make sense? We happy?
Yes, sir, I got it. Thank you.
No problem. So going back to these two questions, A and C both have a small elastic limit, right? They're vertically above each other. They basically have the same elastic limit. However, A has a larger plastic region, meaning material A, you could change the shape and it could absorb a lot more energy than material C. So the answer should be A. Okay. Right, A has a small, so let's just remove all of this nonsense because I'm going to give you guys this working out. So it can't be B or C. So it can't be B or D because they have a large elastic limit. The elastic limit is later on. So it's between A and D, but D has a larger area. So the answer is A. All right, so question 7. A water pump causes 200 grams of water to be ejected from the nozzle of a garden hose each second at a velocity of 3 meters per second. Which of the following expressions could be used to determine the minimum output power in watts required from the pump? So first of all, Joanne, how are we going to start this question?
So can you just have a minute to read it, please?
Okay, good. Sorry, I was moved too quick.
No, it's okay, sir. So I'm actually quite unsure because, like, okay, they're asking us for the power, and power is equals energy over time.
Beautiful. And that is how you start. Well done.
But
Energy.
from there, I'm confused.
What type of energy does it have?
Work done.
No, as in like kinetic, elastic, gravitational.
Oh, kinetic.
Kinetic, because it's moving. Anything with a velocity, we're going to write that down as a skill
Oh,
set. Anything with a velocity has kinetic energy. Good. So what is the kinetic energy it has?
so we just replace the E with half mv squared over time.
So half mass times velocity squared over the time.
Over time.
So
So it's 200 times 3 squared.
well, first of all, it's not 200 because mass is always in kilograms.
Oh, so it's 0.2.
So yeah, it'll be a half times 0.2 times the velocity squared, right? Which is 3 squared.
Yeah.
Divided by the time. You're probably thinking, okay, but it hasn't given me the time, has it?
Yeah.
Well, actually, it's traveling at 3 meters per second, right? Meaning
Yeah.
every second it traveled 3 meters, and every second 200 grams has left. So what is the time?
2.
1 per second.
Oh, okay.
Because it says each, let's read this, each second 200 grams leaves. So your energy transferred is kinetic energy per second, right? Because and this is another skill set we're going to write down. Any question that involves a rate, you can use, rate means per second, okay? Or per blah, 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 per minute. This is a rate. So any question that involves a rate, you can use time as 1 second, right? So good. So this becomes half 0.2 times 3 squared, which is the same as 0.2 times 3 squared over 2, right, Joanne?
Yes, sir.
Which is D. Okay, question A.
Wait, sorry, but isn't it B though? Because it's 0.2 times 3 squared over 2.
Yeah, sorry. Well done, I didn't even notice. This is why you don't rush. The exams are so like sneaky. Because I saw like 0.23 until I had to be right, but I forgot there isn't a square. Okay, good. So yeah, be careful. Excellent, John. So a model rocket is launched and moves vertically upwards while still burning fuel to give a constant upwards thrust. The fuel runs out and the rocket reaches the maximum height at time t before falling to the ground. Which of the following graphs could show how the acceleration a of the rocket varies with time t if the decrease in mass as the fuel burns is neglected? It's A, B, C, or D.
So is it? I'm not sure if it's C or D.
Beautiful start, Muhammad. Why did you say it can't be A or B?
Because what would an increase in acceleration be? What would you call it?
Increase in acceleration is when the force keeps increasing,
Okay.
right? And obviously, what force is increasing? It's not like there's
Yeah,
10
what force is
newtons and
increasing?
it literally says the fuel runs out, meaning there's no longer an upward force. So what's the only force acting on my rocket now?
Gravity.
Gravity. So there's just one constant force, weight equals mg. That's the only force acting on the rocket. So there's a constant force, so there's a constant acceleration. And this goes back to one of the skill sets we wrote previously. We said, is there a resultant force? If the answer is yes, Newton's second law, F equals ma, there is an acceleration, right? A constant acceleration if there's a constant force. So, beautiful. It's between C and D. Now the question is it C or is it D? What's the difference between C and D? Who could answer that question for me?
Sir, I think it's C.
Why is it C?
Because when the acceleration is 0, that means it reached its maximum height. It's saying it reached maximum height at before falling back to the ground. So before T.
Good. Lovely. So looking at this, at the start, there was a constant upwards force. So a constant upwards thrust, meaning a constant positive acceleration, as we could see here. And then when the fuel runs out, there's just a constant downwards force. So a constant negative acceleration or constant deceleration. So that explains this shape. But what happened? What happened? Okay, no, I'm back. So yeah, D is saying that as soon as the fuel ran out and it started to just experience gravity, it's reached the maximum height. So the rocket's traveling upwards, it's accelerating, and the velocity keeps increasing. Let's say all the way until the velocity reached 100 meters per second. And now the fuel ran out, it's going to start decelerating. Did it reach maximum height? No, because it's getting slower and slower. So it's going to be 90 meters per second, 80 meters per second. It's going to keep getting slower. So it's still moving up. Yes, there is a resultant force downwards and there's an acceleration downwards, but it doesn't mean it's moving downwards. It's not like it goes up, then straight away starts to move down. No, it's slowing down, slowing down, slowing down, slowing down until the speed is 0 meters per second. And then the speed becomes -10. And that's when it reached maximum height. And there's going to be two ways to look at this. The first way, I want you to just imagine a suvat. So I want you to imagine this motion here, right, with constant acceleration downwards. Let's say the initial velocity was 100 meters per second, and the acceleration is -10, right? Meaning every second, the speed or velocity decreases by 10. So it's going to be 100, then 90, then 80, then blah, 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 all the way until it's like 30, then 20, then 10, then 0 meters per second, and then -10, then -20, then -30, then -40, then -50, then -60, and so on. This shows constant deceleration. Did it reach maximum height here as soon as it started decelerating? No, it took some time. It reached maximum height around here. So that is why it started to decelerate first and then it reached the maximum height. Another way to look at this is if we could draw a displacement time graph. So let's draw a displacement time graph of the motion. And initially it was accelerating. So how do I draw acceleration in a displacement time graph, Joanne?
Sorry, can you repeat the question?
How do I draw acceleration in a displacement time graph? Straight line, horizontal line, curve.
So is it a curve?
Good, with
Curve going
increasing
upwards?
gradient. Good, curve going upwards. So it's accelerating, 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 accelerating. Fuel ran out at this point. So now it's going to decelerate. How do you draw a deceleration, Joanne?
It's the same, but like the other way.
Good, so decreasing gradient. All the way until it goes back to where it came from. At this position, let's call it X, this is when the fuel ran out. Did it reach maximum height as soon as the fuel ran out? No, it reached maximum height later. This is the maximum height, the maximum displacement. So just because it started to decelerate, it does not mean it has reached maximum height. It's going to take some time. The speed has to decrease to 0 first, has to slow down until your speed is 0, which you could tell as a straight line, the gradient is 0. So the speed has to be 0 for you to reach maximum height. Raise your hands if this makes sense.
So it's C because it takes time for it to slow down and then reach maximum height,
Yeah.
right? That's it.
Beautiful. And it might, it's good to reflect after every question. We spoke about it in the first ever lesson, always be reflecting. So I've reflected by looking at this from two ways, looking at it from a SUVAP perspective and looking at it from a displacement time graph perspective. And as we could see, as soon as it started to decelerate, it hasn't reached maximum height. Question 9, a student walked 12 kilometers in a bearing of 135 degrees, then 20 kilometers on a bearing of 340 degrees. The diagram is to scale. Which of the following could represent the final displacement of the student from his starting point? The A, B, C, or D?
B.
And how did you do
Yeah, B, sir.
How did you do B? Draw it tip to toe, right? So let's
Yeah.
draw. And it's to scale, so you could obviously make it like as accurate as possible. The to scale, clearly, so we drew the vectors tip to toe. Now we're going to draw, because vectors, this is what you do in vectors. Draw the resultant, so from the start to the finish. This is the resultant. This is clearly B. Why is it B and not D? Because the diagram is to scale. And look at our diagram, right? It's clearly closer to B than it is to D. If the diagram wasn't to scale, then for all we know, it could have been D as well. So the answer is B. And this is just a vectors question. So the skill set here is remember when dealing with multiple vectors, the resultant can be found by drawing them tip to tail. Okay, question 10. A lift moves upwards from rest with acceleration A. A student of mass 70 kilograms standing in the lift exerts a force of 800 newtons on the floor of the lift. Which of the following could be used to determine A? Okay, I'll tell you how you should start this question. You should start this question by noticing there's an acceleration, so there has to be a force, Newton's second law. Again, so we're going to start by writing F is equal to ma. There's acceleration, there has to be a force. And the mass is 70 and the acceleration is a, so F is equal to 70a. Now the question is, what is F? F is the resultant force acting on the student. So now you have to consider what are the forces acting on the student. So let's draw the student. What are the forces acting on the student? Well, first of all, the obvious one is there's going to be mg, weight pushing him down. What is there any other force acting on him?
There's 800 newtons upwards.
800 newtons upwards. And where did you get this from?
Newton's third law.
Newton's third law, beautiful. So as we said, remember we're talking about Newton's third law pairs. If he exerts a force of 800 newtons on the lift, that must mean the lift is also exerting a force of 800 newtons on him. Now, we're not going to consider the 800 newton exerting on the lift, because I didn't ask you, okay, what's the resultant force or what's the forces acting on the lift? We just care about the human. So forget about what he's doing. You just have to consider what's happening to him. And what's happening to him, there's weight pushing him down and there's the lift pushing him up. Yes, he's pushing the lift 800 newtons downwards, but you're not going to include that. Just like when someone's on top of the earth and you say there's mg. Yes, there's mg down, but guess what? There's also mg pushing the earth up. You don't go and start considering what the earth is doing. You just care about what's happening to the human. And what's happening to the human is weight is pushing him down and the lift is pushing him up at 800 newtons. And we know this from Newton's third law. So what's the resultant force? It will be 800 minus mg. I know 800 is bigger because he's accelerating up. And also I know what mg is anyway, right? It's 70 times 9.8. That's less than 800. So yeah, the answer will be C. We happy? Isa, Muhammad, Faizan, does this make sense?
So I can explain it again.
Yeah.
Okay, I'll explain it one last time. So I realized this is Newton's second law question because it spoke about acceleration, right? So I started by writing F equals ma. The resultant force is equal to mass times acceleration. The mass of the student is 70. The acceleration is a. Now, I need to know what is the resultant force acting on the human. So I need to know what forces are acting on the human. I know that there's mg pushing him down because of gravity. And I also know there's 800 newtons from the lift pushing him up. Because if he's exerted a force, and it says in the question, he exerts a force of 800 newtons on the lift, that must mean the lift is exerting a force of 800 newtons upon him. So what forces are acting on the human? 800 newtons up from the lift and weight mg down due to gravity. Does that make sense? So the total force is 800 minus mg. That's the resultant force. So 800 minus mg is the resultant force, is equal to 70a. Does it make sense now?
Yeah, I got it. Thank you.
All right, so let's begin section B. So a child is standing on a skateboard. And by the way, there's so much skill sets involved in this question that you guys could write down. So much little things that are used in so many other areas of physics. So a child is standing on a skateboard and both are stationary. The child throws a ball forward at a high velocity and the child and the skateboard move backwards at a low velocity. Explain in terms of momentum why the child and skateboard move backwards at a lower velocity. So have a go, try formula answer. Once you have an answer that you think is worthy of 4 marks, please share it with me.
So I think I have an answer.
Go for it.
So because the conservation of momentum, because there's a conservation of momentum, the momentum of the ball and the momentum of the child on the skateboard are the same. So because momentum is mass multiplied by velocity, the mass of the ball compared to the mass of the child, so the mass of the child is greater.
Why are they the same?
And
I'm gonna have to stop you and say, why are they the same?
why are they the same?
You're right, it's to do with the conservation of momentum, but also something else. What was the momentum before?
0.
Good. Because the momentum before is 0 and they're traveling in opposite directions, that must mean they have to have the same momentum. But if they're both traveling in the same direction at this beginning, it doesn't have to mean they have the same momentum. So momentum is always conserved. Then we're going to say the initial momentum is 0 because nothing was moving. Now carry on, please.
Wait, so can you say that again? Because I didn't think of that. It's because they're both stationary, but you said if they're both moving, then what?
So let's say I had something moving at 3 meters per second, okay? And it collides with something moving at 1 meters per second. And after the collision, they both stick together and move at, I don't know, like maybe 1.4 meters per second, right? That does not mean that the momentum of this, as in like the momentum of one ball, was equal to the momentum of the other ball after. It's the total momentum before is equal to the total momentum after. That is true, but it doesn't mean the momentum of an individual ball was the same before as it was after. Or the momentum of this ball is the same as another ball. So yeah, this question, the reason they both have the same momentum is because initially it was 0, and after something was traveling to the right. So the only way to get 0 is the thing traveling to the left has to have the same exact value. That's why it's important to say the initial momentum is 0 in this question.
Oh, okay. Yeah.
Carry on.
So then it's basically just because, so if P equals, so P equals mv, and because they have different masses, the ball has a small mass, so it's going to have a big velocity. The child has a great mass, so it's going to have a small velocity, and that's why it moves backwards.
Just going to slightly rearrange what you said. So the momentum of the ball has to equal to the momentum of the child and skateboard. Put in brackets, opposite directions though. So any sort of mention that they're traveling in opposite directions is fine. And then, as you said, as the mass of the skateboard plus child is larger, the velocity has to be smaller for it to have the same momentum as the ball. Does that make sense? So good. The child and skateboard has a momentum mv, and the ball has a momentum mv, and they have the same momentum in opposite directions. The only way it's possible for it to have the same momentum when the mass of this one is larger is by it having a smaller velocity. Okay. And that will be your 4 marks. So what skill set do we get from this question is just, I guess, to remember if the initial momentum is 0, mention that. talk about conservation of momentum, and talk about if something has a larger mass, it must have a smaller velocity, or if it has a smaller velocity, blah, blah, blah. And that's how you get the marks. So that's the skill sets. You could write it down in your own time. And do we have time for this question? We'll have a go. I'll give you 3 minutes to read it and at least begin it. There's lots of skill sets involved for this question. And if you don't have just one of the skill sets, you won't be able to answer it, or you won't be able to get full marks. Okay, who thinks they know how to at least start this question?
So I did it. I got an answer, but I'm pretty sure I'm wrong.
What was your answer?
I got 86% efficiency.
That could definitely be right. Why do you think you're wrong?
And then, so you can check it if you have the mark scheme.
83. Is that what you said? Well done.
No, I said 86.
Okay, let's cover it. Anyway, how do you start this question? Me, I care more about like you starting how I'm teaching you to start every question. This is a efficiency question, so you're going to have to start by writing down the equation for efficiency, which is percentage efficiency is equal to useful energy or useful power or whatever. So useful energy, but there's nothing that gives me time, so there's no way I could get power from here. So there's only I could only ever get energy. So useful energy over total energy multiplied by 100. Now, none of you have an excuse to not start like this. This is how I want you to start, and this is how we start every calculation question. Write down what equation you're going to be using that's relevant. There's only one equation for efficiency, so this is very easy to start. Now the question is, what is useful energy and what's the total energy? So let's start with the useful energy. We are trying to move a box upwards. So the useful part is moving the box upwards, right? That's the purpose of this machine. So the useful energy is the work done in moving the 50 kilograms upwards. And this is actually like almost like a general rule. It's like 90% of the time, the useful energy is always the work done. Because for any machine that involves movement, like a car or an airplane or a lift or anything that involves movement, a lift, a crane, using a spring to open something, the useful energy is the movement, moving an object from place A to place A to place B. And the energy involved in movement is called the work done, which is the force times the distance. The force and distance have to be in the same direction, okay? So this is the useful energy. The total energy is where did you get the energy from? How were you able to get the energy to lift this 50 kilogram mass upwards? Where did the energy come from? Who wants to answer this question?
From the 8 kilogram mass.
But what's the energy?
So it's gonna be force multiplied by the distance, 2 multiplied by
No. The energy came
The
from the
gravitational potential.
Excellent. It came from the gravitational and potential energy of the 8 kilogram mass being 2 meters above the ground. So the total energy, where did I get the energy from? Well, I got the energy because I had the mass above the ground, right? It had gravitational potential energy. So total energy in this case is your gravitational potential energy, which is mgh, which is 8 times 9.81, and it travels a distance of 2 meters. Slap this in your calculator. Let me do that quickly. I get 157 joules. Okay. This is my total energy. Now, my useful energy is the work done. This is going to be slightly more difficult to solve because I need the force and I need the distance. Well, first of all, what is the distance this 50 kilogram mass is going to move?
2 meters.
2 meters, right? If this moves 2 meters, the mass is going to move 2 meters. Kind of like if you have a car towed to another car, right? They're attached by a string. If this car moves 5 meters, this is going to move 5 meters. It's not going to move 10 meters. A lot of students would have probably, for some reason, put 15 meters by accident. Like, oh, it traveled 15 meters. No, how can it travel 15 meters when the mass only traveled 2 meters? It doesn't make any sense. So yeah, I know the distance is 2 meters. The question is, what is the force? Well, there is a force, and you want the force in the same direction. You want the force in the same direction as the distance, because it's traveling 2 meters along this plane. So you need the force in this plane as well. Now, this is going to involve a new skill set that I'm going to teach, and this is called the inclined plane. And in the inclined plane, if you have an object in an inclined plane, there will always be gravity acting downwards. Gravity is mg. So there's mg acting downwards. Let's assume this is theta. Or let's put a value so it makes even more sense. Let's say this is 20 degrees. Let's say this is 20 degrees. If this is 20 degrees, I've just made a triangle where this is the right angle. This has to be 70 degrees. Now what I'm going to do is I'm going to draw a line perpendicular to the surface, to the plane. So this is perpendicular. This is at, as you can see, this is at right angles. And then I'm going to draw another line starting at wherever the force mg ends. That's parallel. This is now parallel to the plane. Here, the plane's in this direction. If that's, and this is another right angle. There's another right angle here. If that's 70 degrees, this has to be 20 degrees. Now, all of a sudden, I have a right angle triangle with the hypotenuse and an angle. So, of course, we've done this many times in vectors already. So let's do that again. So you've got a right angle triangle where the hypotenuse is mg and the angle is 20 degrees. This is going to be mg sine 20 because it's opposite the angle. And this is going to be mg cosine 20. Now I know that yes.
So you said, for example, 20 degrees. So they didn't give us exact value, right?
So
Of 20 degrees.
Yeah. So if instead of 20, it was 50, it will be 50. If it was 40, it will be 40. If it was theta, it will be theta.
So for this question, you can just choose any value.
For the angle, no. You have to work out the angle, or the question will give you the angle. The angle is needed, otherwise it's not solvable.
So how did you work it out then?
Oh, I just guessed. No, I didn't. I just made up a value. So I could explain why if this is 20, this has to be 20. But it's not. I'm just giving you a general question. This is not the question from the exam.
Oh, okay.
So yeah, now all of a sudden, I have a horizontal component of mg. The horizontal component is the force that's going to act in this direction, right? It's the force pushing or pulling the what's it called? The mass over there. I know there's going to be friction opposing it. If this force is greater than the friction, it will slip, it will fall down. If friction is greater, it will stay where it is. Anyway, this horizontal component is mg sine 20, meaning there's a force in this direction of mg sine 20. And there's a vertical component going downwards of mg cosine 20. Now that's not really relevant. That's not causing it to move. That's just acting here, right? And I know there's going to be a Newton's third law of mg cosine 20 going upwards, right? This is the pair. This is the reaction force. For every action force is equal and opposite. But that's not relevant to this question because I just want the force that's in the same direction as the distance. Remember, the distance was along here, and now I have the force in the same direction as the distance. I could now do work done is force times distance. It would have been tempting to just say mg times distance, but this isn't the force in the same direction it's moving. You have to work out the force in the same direction it's moving. That's why I had to resolve my vectors and work out the horizontal component. So now going back to the question, I need to know what theta is, otherwise I can't do anything. How can I work out what this angle theta is?
So you can do sine 2/15. Shift sine 2/15.
So sine theta is opposite over hypotenuse, which is 2/15. So sine theta is equal to 2/15. I'm going to leave it as that. I'm not going to work out theta because I don't need to, and I'll explain why soon. So let's now resolve. So this is going to be, there's going to be mg, which is 50g downwards. There's going to be a horizontal component of 50g sine whatever theta is, and a vertical component of 50g cosine theta. I don't care about the vertical, it's not in the same direction as the distance, I just care about the horizontal. So I know there's a force of 50g sine theta. And sine theta is 2/15. So that's the same as, so we said it equals force times distance. The force is
Wait, so I have a question.
50g 2/15. Just 2 seconds. So 2/15 is the same as sine theta. That's what we did above here. Sine theta is 2/15. This is 50g sine theta, so 50g multiplied by 2/15. This is the force in the direction of the distance. Yes, what's your question?
So when we apply the mass, the 50 kilograms is gonna move to the right. So aren't we supposed to work out the force moving in the direction? The force moving in the direction of the object. So it shouldn't be like the force.
Then you're working out, all of a sudden you're working out the total energy. I'm going to answer it like this. I want you to think about the following. In order for me to make this 50 kilogram object move, I need to apply a minimum force of 50g sine theta, right? That's the minimum I need. Otherwise, would it ever move?
No.
So this is the force required. This is the minimum force required to start moving at a distance of 2 meters. And this is the force that is used in force times distance. This is like the force, the minimum force required for it to begin moving, or for you to begin moving. So that is the force used. So the force is 50g sine theta, or 50g 2/15. Distance is 2 meters. So 50 times 9.81 times 2/15. Let me put that on my calculator quickly. Let me just check the mass scheme to speed things up. So force times distance, 130.8. So you will get 130.8 joules. That is my useful. So let's go back to the equation of efficiency. Useful over total times 100. 130 over 157 times 100. According to Mark's scheme, you get 83%. So he's a liar. It is not more than 90% efficient. It's 83% efficient. So just write a conclusion. He lied, blah, blah, blah. Or don't say he lied. Just say his maximum efficiency was less than 90%.
So
Okay,
can I take a screenshot of your working out?
I'm going to send you my working out on the group chat.
Okay. Thank you.
So I just want to end this session with what were the skill sets involved in this question. The first skill set involved is an efficiency question. You start by writing efficiency is useful over total times 100. That was a skill set involved. A second skill set is to realize that the useful energy for moving objects is work done. That's the second skill set involved. This skill set might be used in another question that's very different. It's just it's a separate skill set. And every physics question is a combination of skill sets that once you get in your long-term memory, you'll know how to answer questions really easy. So useful energy is work done, which is force times distance. And this is for any appliance, any system, I guess, any system that requires movement, right? In this one, you wanted to move it up a steep hill. So obviously, the work done is your useful energy. The third skill set is the total energy. Total energy. What's the total energy? You have to ask yourself this question. Where did you get the energy from? Where did you get energy from? Was it from the kinetic energy? So maybe something had kinetic energy. That's where it got the energy from. So was it from half mv squared? Was it from gravitational potential energy, like in this question? Was it from stretching a spring? So half Fx squared, right? Did you get the energy from the spring? Did you get the energy from, I don't know, let's say the power output of an engine? So was it the engine converting chemical energy? And I know 700 watts. So I do energy is equal to power multiplied by time. Did I get the energy from the engine? So power output of an engine. So you have to ask yourself these questions. And honestly, it's very easy to know where you got the energy from. Just look at the question. So power output from engine. So that is your another skill set, is to realize the total energy. You have to ask yourself the question, where did you get the energy from? In this question, we got the energy from something being above the ground. So from gravitational potential energy. Another skill set, yes.
So for the first one, what did you write for any system that requires what?
Oh, I didn't finish the movement, sorry. Thank you for reminding me. So aeroplane moving, a lift, an escalator, anything that the aim of the system is to move, the useful energy is the work done. If the aim of the system wasn't to move, it was to heat something up, then obviously you can't do work done, can you? It will be something else. Okay, another skill set we learned. Yeah.
So for total energy, couldn't you also use force multiplied by distance? Because then you do
MGH comes from force multiplied by distance, because the force is the force of gravity. What's the force of gravity? mg, right?
Yeah, mg.
And the distance is the height. So yeah, they're the same thing.
Okay, yeah, because I said that earlier and you said I said no.
Did I? For the total?
Yeah.
Sorry, was a mistake. Okay, if that happened. Okay, so another skill set is that when you're doing work done is force times distance, you need to realize the force and the distance have to be parallel. They have to be in the same direction. Another skill set that's always need to understand. And then finally, can use trigonometry, can use trig to work out angle. That was a skill set involved. And actually, there's just one last skill set, and this is the one, I don't know if I even have space to draw it. I'll try to fit it in. And it's the incline plane skill set. So let me draw it here. And that is for anything in an inclined plane. Where there's has a weight mg. The horizontal component is mg sine theta, and the vertical component is mg cosine theta, and theta is this angle here. So we had to understand this as well. And these are all the skill sets required. And the reason I like to do this is because I hate when students like say, I don't know how to answer this question. I won't be able to do it in the exam. But the truth is if you had all these skill sets in your long-term memory, then you can answer this question. It becomes easy all of a sudden. Nothing's difficult because you know these skill sets. But if you miss just one of these skill sets, then yes, all of a sudden the question becomes difficult. But even then, if all you did was, like said, percentage uncertainty is useful over total, useful is work done, total is GPE, you would have scored 2 out of 4. And that's really good, right? Because remember, some exams, you only need 60% for a star. So you need to start picking up marks wherever you can. Okay, does that make sense? We happy?
Yes, sir.
All right, I will see you all on Thursday.
Okay.
So I have a quick question.
What's the question?
Sir, for the for where you wrote 50 g sine theta acting like the resistive force of 50 g sine theta, and then you have the force forward 50 g sine theta. So if that was the case, then the 50 kilogram weight wouldn't move, right?
Yeah, it wouldn't move if that was the case. Yeah.
But using that because it's the minimum value. So
yeah, we're using that because that is like, yeah, that is kind of what we need. Even if you had 0.00000001 newtons more than that value, will it move?
Yeah,
Will it travel a distance of 2 meters eventually?
eventually, yeah.
Yeah, so you can do work done force times distance, and you can use that as a rough estimate of the force. Does that make sense?
Yeah, okay.
Okay.
Okay, sir. See you next week.
See you Thursday. Bye.
Right, sir.